Yes. Thank you. So we start again from where we left yesterday. So I remind where we were. We computed the loop integral with the top here. These are actually two diagrams which are summing, and that's the reason why at the end there is a factor of 2 here, which cancels with the factor of 2 of the normalization of the SU3 algebra. Okay, so we don't have factor of 2 at the end. So the other thing that we notice is that when we take the trace, we need to pick up a mass, one of the three masses, which is here, here, or here, one of them, we have to pick it up, because otherwise the trace is 0. So physically, what it means, remember that the QCD interaction are vectorial. So they couple left with left and right with right. Okay? So the Higgs interaction couple left with right. Okay? So when you are here in a loop, for example, you start with left here, then you hit the Higgs, you are right, then you go here, this conserves chirality, okay? So this conserves chirality, and then the chirality don't match, right? Because the Higgs changes the chirality. So you need a mass insertion, which is like an interaction like with the vacuum, like here, right? You need a mass insertion to reestablish the chirality. And that's the reason why physically you need a mass term in front. Otherwise you get 0. If there is no mass, you get 0 independently. Okay, so it's a spin flip correction, insertion. You insert a mass term to correct for the flip of the on-shell Higgs which is produced. So this gives the dependence on the mass, which the one with the coupling gets a mass squared, and then there is an integral on Feynman parameters, okay, which we'll leave it there, it's very simple. And then we extract the mass dependence there, and we noticed yesterday that there is this mass term, this one, which cancel. So the dependence on the every quark mass is only in the integral. So we go and check what happens in the integral. Okay, so when the mass of the quark is very large, so this is A goes to 0, right? This is a ratio. So when the quark mass is higher than the Higgs mass, this goes to a constant of 1/3. On the other hand, if the quark inside the loop is much lighter than the Higgs, you have another limit, and this gets you to minus, so notice this minus here. So minus 1 over 2a log square, which if I substitute with the ratio, so it's 1 over a, so it's mq over mx squared, log square mx squared over mq squared. So when the mass of the quark goes to 0, we said, right, the whole thing goes to 0, and that's okay, because I cancel everything, but I knew that this goes to 0, right? The power in front wins over the log. So when for the big, for example, if that is the top that we are looking in the loop, it goes to a constant. If it's a bottom, it goes in this direction, okay? And it has opposite sign. So the bottom in the loop is there, right? Like with the top, this is brother or below, right? The little brother of 5 GeV mass is there in the loop, but it contributes with the minus sign. Okay, so if you remember again the anomalies, right? It has nothing to do again, but the upper component, lower component contribute with the opposite sign. Here, it's nothing to do with the hypercharge. The SU2, right? Charge, but it has to do with the mass. It's just because the bottom is lighter than the Higgs that it contributes with the minus sign. But as a mnemonics, they work in the same way. So what? Okay. Of course, the bottom is much less important than the top at the end, and so that it contributes in a much smaller number. So if I then go back to the top, I find something apparently contradictory with what we learn, right? So our intuition, that in the large mass limit, so when you send the top mass to infinity, so you would say you decouple your top from the standard model, this term is there, right? It doesn't go to zero. It doesn't scale to zero. And actually, it gives rise to an interaction of this type. Okay, so this is a point-like interaction. There is no structure, right? It's a Feynman. It looks like a Feynman rule. Exactly, right? So the Feynman rule, the tensor structure will be this one. This is the color, which is conserved because X is a singlet in color. So the color that enters is the same as it gets out. Okay. And then you have the polarization vectors for the gluons. And then there is this coupling here, which remembers about the structure, right? So you get an alpha S, which remembers the fact that there was a loop here where the gluon coupled to the quark. So there are two coupling, so you get alpha S in the rule, right? You don't get GS, you get GS squared in the Feynman rule. And then finally, and very importantly, you get V here, okay, which is coming originally from the Yukawa. So this V is the normalization of the mass that you are canceling. Okay, so you find that this Feynman rule, okay, here as dimension 2, but then there is also this factor V in front. Okay, so it's a strange rule because the scaling with energy, right, is suppressed by 1 power of V. Okay, so you have, yes?
In the limits that you write down, is the ratio, shouldn't it be exactly the other way around? Like when A goes to 0, also the ratio of the masses goes to 0, right? That's exactly the definition.
I'm not sure I understand. Which, you're looking at this?
Yes, I'm looking at the line beneath the arrows.
Ah, yeah, it's the same. I mean, it's like this is the same as this. No, yeah, you're right. Sorry. No, yeah, right. Sorry. Yes, I changed the last moment. I want to have MQ, but you're right. Thank you. Please correct. I mean, I made many mistakes in the Blackboard, as you have realized already. So just tell me, because for the other student that might not notice it, so it's very helpful. Thanks. So where were we? So we are here. So you had a few hours to think about. So who has an answer, or who wants to propose an answer for why this behavior actually, even though it doesn't respect our first intuition, is actually correct?
As you increase the mass, you also have to increase the speed of the mass.
Very good. So in the standard model, question: how many scales there are in the standard model? So if someone asks you how many scales in the model are there, your answer is 1. Right? There's no other scale. There's only V in the standard model. And everything else comes from V. But there's only one scale dimensionful, and is coming from here, right? So there's only one scale. Yes. Yeah. Very good. Those are somewhat generated, right? Somewhat by renormalization or in general. I'm talking about the. That's very good observation. Let's say a tree level. Okay. Let me take the tree level leading order point of view. So there is only one scale in the Standard Model, which is mu. Okay. Which we trade for v at the end. Okay. So there is only one scale. Now, if you look at the theorem of Alpecast and Carnothonis on the decoupling theorem, it tells you that you have to have decoupling, you have to send a dimensionful parameter to infinity. Right? So when I say that the mass of the top, I send the mass of the top to infinity, I have to say what I'm really doing. What am I doing in the Standard Model if I say that the mass of the top goes to infinity? I have two choices. Either I send V to infinity, but then I send everything to infinity. Even the Higgs goes to infinity, right? So all the Standard Model moves because there is only one scale. Okay, so that's not what we meant, right? When we say that we want to send the top to infinity. What we would like to do in our mind is that since the top is much heavier, I keep sending it higher and then I leave everything else there. So I cannot touch V. I mean, I didn't want to touch V in my mind when I say the top decouples. Okay, so what is the other way? The other way is to, so either you send V to infinity or you send YT to infinity. But that's not the decoupling theorem. If you send the coupling to infinity in a normalizable theory, you don't get decoupling. Okay? You get a strongly interacting theory. It's just a totally different animal. Okay? So that's the reason why we cannot send any of the particle in the Standard Model to infinity. However, if you remember, we are doing it from time to time. But if you think about it, what we are really doing is to do that in QCD or in QED, but not in the electroweak theory. So if I only consider QCD, for example, the mass term in QCD is just m phi dagger phi bar phi, and then I can send the top to infinity there, and then I do the matching at various scales and so on. But in electroweak theory, I cannot, because at some point the theory becomes strongly interacting. There is actually a limit which comes from unitarity that tells me that this number cannot be larger than 4 pi, roughly speaking. No coupling can be very large, because otherwise you should change your degrees of freedom. Okay, you should change the way you describe the system. So there is, in the Standard Model, you cannot send any of the masses to infinity. Okay, so if you try, what happens is that you generate an operator. Okay, so now I do it somewhat anyway, right? I mean, I'm doing this. I'm just numerically checking it. So what is this? This is nothing else than an operator of this kind, which is the one that Ian mentioned. Okay, where I couple the Higgs to the field, the kinetic term of the gluon, right? And this is the first diagram, that the first Feynman rule that I get from here. And this is a dimension 5 operator, okay, with V, vacuum expectation value, as the scale of, it's like lambda in the EFT. So this is a theory which somewhat is valid up to V. So it's a low energy theory where if you want, the top is the same, is of the order of V. So I work at low energy, where the top I never excite it. I integrate out in a sense, but the scale that I get is already automatically there, is the same scale V. It's not a new scale, because that's the only scale I have in my problem. So I can think, I can always think in the standard model of looking at it at very low energy, like I do in the Fermi theory. Okay, Fermi theory is still a standard model, but at low energy, and I integrate out particles in the standard model. Okay, so let me do again what was mentioned at the beginning, right? So if you take Fermi theory, right, you have GF over square root of 2, and then a 4 fermion operator, right, where you have the W here. So at low energy, the standard model process at low energy looks like the effective field theory. We said this already, right? And this thing here is G squared over minus G squared over MW squared, right? So if I ask you what is the scale of, in the effective field theory, what is the scale of my lambda, what is my lambda, you would say is MW. But if you think about the standard model, it's not MW, right? Because the weak interaction at low energy don't know where the MW is. We cannot predict MW by the decay of the muon. We don't know where it is. Why? Because if GF depends on MW, so we match this, right? And this is GF, right? So let's say, well, if I know GF, I know MW. No, it's not true, right? Because MW in the standard model is 1/2 GV. And this is 1 over V squared. There is no information on W. The only information we get from the muon decay is where is V, not MW. And then if you want a theory which is weakly interacting, MW must be lower somewhere before V. That's the only thing we know, if G is smaller than 1. Okay? Is that clear? So GF, right, is related to V, not to the mass of the W. And that's how we get V without, from the muon decay, right? Without doing anything, because from the muon decay, we have, as we mentioned already, mu to the 5th, right? And this, I never remember, is it 2 or 3, something, n. And so you get from the muon decay, you extract GF, and from GF you get V. So the vacuum expectation value of the X, we knew it since a long time. I'll come back to that because it's important. But I want to stress the fact that when you integrate out a standard model particles, you always get to V at the end as a scale. Okay, which is the same thing here. You get to V. Is that clear? Okay, very good. So now I can write this theory. Now you would say, well, but this theory is not SMEFT because I'm using age. Age is not SU2 invariant. It's inside the doublet. It's one component. So if I write something in terms of one component, it's certainly not gauge invariant. Okay, so what is actually, and then it's dimension 5, and we learn that there is only one operator of dimension 5 in this SMEFT, in this Majorana mass operator. So what really operator is this in this SMEFT? And then you see, right, easily, let's say, right, that the corresponding operator is in this SMEFT, is this one, which I call, so this will be an operator now of dimension 6, and this one I call O phi G. I will call it this way in the following. Okay, so you see that when phi gets a vacuum expectation value, right, you get, if you get a term which has 2 powers of v, is v squared g, which does nothing. It just renormalize the kinetic term for the gluon. And then you have a mixed term, right, age v. If the scale of new phasing is v, then you have v over v squared, and you get this one with an arbitrary coefficient if it's an operator, while in the standard model you get one specific value, because you have a model and you are integrating out, so you know everything. It's not arbitrary, it's not new physics. It's physics that we know. So the coefficient in front we can predict if I'm integrating out standard model states. Is that, are you convinced? Does this, yes. Exactly, that's what we will do next. Thank you very much. Okay, so this is my theory now. So the idea is, okay, I integrate out somewhat the top. Why I would do that? Well, doing loops can be fun, but can also be very expensive and very difficult if I want predictions which are more accurate. Because now to go next to leading order in the Higgs production, I need to go to 2 loops instead of 1. So I lost, at the starting point, I lost 1 loop right there, right, in the accuracy, because I start with something in 1 loop, and then to increase my accuracy, I have to go higher and higher. So people have said, well, why don't we use a theory? Let me call it X effective theory. This actually is meant for some other theory, really, but let me call it this way. So if you have X in GG operator, this one that we were mentioning, then you generate Feynman diagrams, Feynman rules, sorry, for all interactions. Exactly as in QCD, right? This will be the propagator, kind of, right? But then you insert a field, and this is the rule, right, apart from the epsilon. But basically, this is the Feynman rule. Then you would have this one, and this you get the Feynman rule for 3 gluons. Okay. Then there is a structure here, which is P minus Q, nu, G, rho, sigma, blah blah blah. Right. The QCD vertex for 3 gluons, and here you get FBX, FCDX, and then a G mu nu, G rho, blah blah here, and it's the Feynman rule for gluons. It's the same theory. These are the same Feynman rule, apart from this one, which is not there in QCD, right? But the other structure are the same. The only difference is that this X is dynamical, so it gets also momentum. So it sucks some momentum in one direction with respect to QCD. Okay? So you get a theory which really, when I draw this, I really mean this thing. Right? When I draw this, I mean this, somewhat. And so on. So there is a loop which is shrunk. Okay, there. So of course I gain an enormous advantage in computation, because now from a theory with a loop, I go to a theory which is 3-level. The Feynman rules, I know them very well. Okay, so I can code them up in a leading order computation, one of these automatic codes where I get amplitudes for free. That's easy thing to do. And then I compute, right? I can compute anything that has the Higgs in the final state from gluon fusion, not doing even 1 loop. Okay, so what is the question? If you're actually interested in comparing with data, this looks great. looks a fantastic simplification. Well, does it work? Right? I mean, is it a good approximation? Because the top mass is not infinite. It's 172.5. The X is 125. So I expect some corrections here. But the corrections, I know how they scale, but I don't know the coefficient. And I don't know if they are independent on the phase space region, right, of this simulation. So let me do it. So let's do it, right? It's in the notebooks as an exercise. So let first compare glue to Higgs, our cross-section level, with the true loop one. Okay? So we do this. We compute it with effective field theory, point-like interaction tree level, and we compare it with the loop-induced process, which is the true one and leading order, and we see how it goes, how it fares. Okay? And what we do as a first exercise, we compute the simplest possible observable, which is the cross-section. Okay? For producing a Higgs. I gave you all the formulas yesterday. They are in the notebook. So you run the notebook and you get this curve here. I hope you can see. So the red, so again, the only parameter that I can change now is the mass of the Higgs, or I can change also the mass of the top, in fact, right, in my game. But since I'm integrating the top out, I'm taking the limit very high, okay? So the only thing I'm changing now is the mass of the Higgs. So this plot is not a physical plot, it's a theory plot, assuming that I've not discovered the Higgs yet, and I can change its mass, okay? Yes? Top mass is the top mass is the physical one, 172.5. Yeah. Yeah. In the true, so in here the top mass is 172.5 GeV here, and I'm changing this guy mass, and that's the x-axis. Here I don't have any top mass, and only changing the mass of the Higgs. Okay, so the red line, you see, it goes, the cross section, if the Higgs increases, goes down. Why? Why it's more difficult to produce a Higgs which is heavier? Who knows? What is the relevant figure here? Why is going down the cross section if the Higgs is heavier? Is the gluon PDF, right? Is the fact that there are less gluons with high hex in the proton, and there are more gluons at small x in the proton. Okay, so the large number of gluons in the proton comes from small x. So if I do, if I look at the number of protons and high energy, you see, is this mass of the Higgs is this thin line red, but it's divided by 10. So the gluons are many more than anybody else in the proton at these scales. But you also see that they go down like a rock, right? They really, with X, if you ask a lot of fractional momentum to a gluon, it's very rare in the proton to have one gluon that gets most of the momentum of the proton. You have so many gluons at small x, but very little gluons at large x. So that's the reason why having a heavy Higgs is difficult, because you have to pick up a lot of energy from one gluon on one side and from gluon on the other. So the probability goes down. Okay? So it's going down because of that. Then you see that if the Higgs is light with respect to the top mass, the two curves, the blue and the red, are the same. So this says that this approximation works super well when the Higgs is light. Okay? So our Higgs is here. So it's exactly where it starts to gets slightly different in this plot, right? But it works very well. So if I have to compute a cross-section, inclusive cross-section for the X of 125 GV and then HC, this works super well. So I'm happy. If I had a Higgs which was heavier, of course this gets worse and worse until you get where? Where something happens which is weird, right? There's this camel hunchback thing here. What is it? Who knows what? So why the top loop does this strange shape at 350? Twice the top mass, fantastic. Yes. Twice. So why something weird happens at twice the top mass? Why the cross section is enhanced at twice the top mass? It's a cut. It's a cut, right? What does it mean? It means that these two tops inside the loop can get on shell at that point, right? So instead of being like a true loop where everybody inside the loop is virtual, the cut means that this process becomes a rescattering, really, right? It gets a phase, it gets an imaginary component, which is really the production of a glue to TT bar, and then the TT bar fused into a Higgs. And this is possible if the Higgs is heavier than the two tops. Otherwise, you cannot. Okay? So at that point, this thing, technically we say that the loop gets an imaginary part. Then when you square the loop, the real and the real square, but also the imaginary and the complex conjugate gets together. So this thing is the imaginary part which opens up and is added up there, and you get a bump. Of course, there is no bump. I mean, there is no bump here at the end because you are producing one Higgs on shell. So the only thing you can do is to measure the cross section. That's it. In this hypothetical world where the Higgs is heavier. Yes.
But why is it in this case like a nice smooth function? Like I would expect that if it's, it's being virtual, and such that if it can, if it's not can be on top, why isn't there like a chunk? Why does it like?
So this is not a physical plot, right? I mean, I'm plotting an infinite number of different universes, but we live in one of these plot. We live in one here, right? We live either here or we could have lived here, and the only thing that you would measure is the point blue or red. So there is no, it's not a differential distribution, okay? And that's important to know. And we will plot differential distribution. This is not a differential distribution. So once you put the mass, you live here. So one calculation is correct, the other is wrong. That's it. Or both of them are good approximations. Okay. So what I'm saying is that if you have to compute this observable, be careful. It's an observable dependent statement. This observable, the total inclusive cross section, we are good. Okay, in our universe, where the Higgs is 125, we are good because the red and the blue are close. So if I want to be very precise, I will put corrections. But for this observable, we are good. Now, what is, so when I do a leading order computation, I have glue to Higgs. So the Higgs, actually in this leading order approximation, the only thing can go is like this way or this way, but it cannot have any transverse momentum. And this order in perturbation theory, right? Because I don't have any way of giving a kick. So how do I give a kick? What if I want to see a Higgs with a transverse momentum in itself, right? So what diagram I need to include if I want to study the PT, the transverse momentum distribution of the Higgs and the HC. I need at least what? Something that recoils against the Higgs, which in this case can be a gluon, right? So I will compute a process like glue, then glue, and then Higgs on this side. Okay? So I will do a computation, which is the amplitude of glue to glue Higgs. So this is alpha, is one order of alpha higher. So this is a one term in the next leading order cross-section computation. If I wanted to compute sigma and next leading order, I have real corrections, so this is a real correction, and virtual correction. So this one is the real, and then I would have a virtual correction like this, which originally was a two-loop computation, but I'm reducing the complexity to one loop. Okay, so if I want to compute next to leading, I would compute this plus this. I would integrate all over the phase space. Then I know it's finite. It's done again. It's done in the notebook. If you want to try, we might try a bit. Okay, but now I'm not interested. I don't want to plot. I don't want to calculate the cross-section inclusive and next to leading order. I'm interested in another observable, which is the PT distribution of the Higgs. And now this is a distribution, right? So this is something which we can measure differentially at the LHC, right? We see a Higgs, we check how big is this PT, and then we make a plot, a frequency plot of the PT of the Higgs. Okay, so what we are after, I plot here PT of the Higgs, and then I plot d sigma over dpt of the Higgs. This is a frequency plot, and then let's see. So we have one event, we measure the PT of the Higgs, and we put it here, right? And then we measure another event, and we put it here, and then we build an histogram, and at the end we have a distribution, which we measure event, after I collected 1 million events, I can make this plot here. Okay, so it's nothing to do with this plot, right? This is a frequency plot. Okay, so now I can do another check. Okay, I can tell, okay, this is an observable. This is one definition of observable. Very well defined observable, because I'm not, so now I will tell you that something tricky. So I'm not plotting the PT of the jet. I'm plotting the PT of the Higgs. So a leading order for this observable is the same thing, because a leading order is the 2-to-2 scattering, and so the PT of one is the same as the PT of the other. But at higher orders, it's not true anymore. And the PT of the jet, I need to define a jet. But for the PT of the Higgs, I don't need anything. This is a completely very easy observable to compute, completely inclusive. I don't even need to know what a jet is. Is that clear? Yes. Can you speak up, because I'm deaf? Next to leading order. A next to leading order, for example, you can have this. A next to leading order in this observable. So this is a leading order contribution to the XPT. So this is leading order for XPT. Remember, let me write it here. The adjective leading order or next leading order or whatever is associated to an observable. So when you say something, someone saying, I made a calculation for the X and next leading order, it doesn't mean anything. Because you have to tell me which observable you calculated in which order. Okay? So before, when we were talking, I was talking about the total cross-section and next leading order. Now I'm talking about another observable, which is the PT of the Higgs. So the first contribution to the PT of the Higgs in QCD, it comes from this diagram. Okay, so this is the leading order. And then if I go next to leading order, I can get this, for example. Okay? And this thing is obviously problematic, right? You need virtuals here, like this kind, to cancel the divergences that you might have when these two gluons go collinear, for example, one with another, or one of the gluon is soft, right? So if you add this virtual, like this, right, there is still a jet recoiling. So this virtual plus this give for the PT of the X an inclusive infrared prediction, no problem. Okay, so that's the reason I was careful in putting PT on the X, not the PT on the jet. So otherwise, if I have put the PT on the jet, I need to define what the jet is and next to leading order and so on, which will take another lecture. Okay, which we don't have time now. Okay, good. So now I still, let's go back and let's not go into this. So now I have this diagram. So this is the process. Here I have this, for example, diagram. Here I would have even this one, for example. Okay, so now I'm comparing this with this. Different story. Ready? So now we see the result here. Well, I can, yeah, well, let me show you the true thing. Again, now this you can do yourself easily also using one of these automatic codes again. So now we plot a distribution, which is this one. So now it looks like before, but there's nothing to do with before. This is a MAC graph run out of the box, right? So the blue line is the true result, is the loop result, and the green line is the effective field theory, is this one. So what I get is roughly that they agree, and then the after as a tail which is higher than the true one. The true one means the standard model one, the one where the top is what it is. It's not set to infinity. Now you say, well, so you see, in low PT, it works super well, right? But then when you come around 200 and 300, right, start to deviate. There are no bumps here. It's continuous. But you feel, right? So if we have data, and we do have data for the XPT and 300 and 400 GME, you would see that if you have predicted with one theory or the other, you can see the difference, right? When one is wrong and the other one is right, because in real world is this that it passes. This is my approximation here in this study. Is that clear? So now we really need to stress two very important points here. So the first one is how come, physical intuition first, how come they are good, it's so good here and it gets worse here? Why? How would you explain it to your friends? Okay? How would you explain that they differ? Any idea? Well, you can try to build an argument. Okay? So what could be the argument? Well, the argument is that one argument could be the following, right? So imagine that you have a Higgs, and then there is a gluon here, right? Which then recoils again in the Higgs, and the Higgs gets kicked high energy. Now, if the wavelength of this gluon is longer than the size of the loop, the gluon will not see the loop. Should I repeat? So it's a Heisenberg argument, right? So this is a wave. Okay, if its wavelength, right, is longer than the size of this loop, you don't see the loop because it's too small. It's like a radio wave. If you have a small antenna, will not eat it because it's too long. Will not see the resolution. So in order to see the loop, you have to have a wavelength of the gluon of the same order of the size of the loop. So what is the size of the loop? Well, it will be something like 1 over mt, right? Because there are propagators of the top. So the size of the loop is something like 1 over mt. And what is the wavelength of the gluon? Well, the wavelength of the gluon is 1 over the pt of the gluon, right? De Broglie, right? Lambda h over p. So the wavelength of the gluon is 1 over pt, and the size of the loop is 1 over mt. So you will see the loop when these scales are similar. And that's exactly what I find, right? I mean, I see that there is a difference between the shrunk loop and the loop when I have a gluon whose frequency is high enough to resolve the top loop. Okay, so that's the intuitive description, and it works, right? And it works. Then the other observation I can make is a bit more technical, but also even more general. And my question is, if I didn't tell you which curve was which, right? In fact, I didn't, basically, because it's hidden, right? But I told you the colors, and here I said that this was left. Imagine that I show you a plot where I didn't explain anything, and I put the two curves, and I told you one is the standard model prediction, and the other one is the approximation with the shrunk loop. Would you have guessed which one was which? Of course, the answer is you should say yes. Okay. Right? The answer is yes. Why? Right? Who wants to try that? Why I should know which one is without even reading the plot right? So while you're thinking, I'm gonna write, and then I'll ask you. Okay, so of course you're not supposed to know the formula for the matrix element squared by heart, right? But I write it because it's so simple, right? I mean, you have to some many diagrams with the X. This is an effective theory, of course, right? There is V, so it's an effective field theory computation, and it's so simple that it can be written not in half a line. Okay, so it's worth writing. So ST and U are the Mandelstam invariant of a 2-to-2 scattering. And now we said yesterday, what are the dimensions of a scattering amplitude 2-to-2? 0. Okay, so a 2-to-2 scattering amplitude has no dimension. And then we have another important piece of information that, if you remember, when we studied the standard model in class, our teacher always said there is a very important aspect of the standard model with which you actually can build the standard model from scratch, which is what? That the standard model predicts cross sections and amplitude which satisfy unitarity, right? You never violate unitarity. Actually, that's a guiding principle. You can derive everything by asking that your theory is unitary. You can even derive gauge theories, in fact. So it's a very powerful way of organizing the argument. We have not time to do that here. It's for another time. But remember, right, that every amplitude, right, you take you make a partial weight decomposition of the amplitude, and then you know that each AJ, right, it has to be smaller than 1/2 or 1, right? The famous Argand plot. Does it sound a bell? Where you make a partial weight decomposition of any 2 to 2 amplitude, and your stay within this circle to be unitary. So any amplitude cannot be larger than a constant, cannot grow beyond a constant, cannot grow with energy, right? This is our leading argument for which we knew that we had to find something in WW scattering, right? WW scattering, if there is no Higgs, it grows with energy, right? And the Higgs is what leads us to conservation of probability in WW longitudinal scattering, right? Our no-lose theorem with which we built the LHC. So I'm not going to that again, but remind you that's super important, okay? And we should use it anytime when we deal with effective field theory. Because in effective field theory, by definition, there is an upper bound on the validity of my theory, right? So the amplitude can grow with energy because they are not supposed to be valid at any scale. It's an effective field theory, it's bound to fail. And the amplitude might, not always, but normally can reflect that. Okay? So if I do a computation in the standard model, the amplitude cannot behave in a unitarity violating way. It has always to be such that is well behaved and high energy. However, in an effective theory, this is not true. So let's look at the amplitude here. So the dimensions of the amplitude overall must be 0. But in fact, you see that there is V in front, which will be lambda in an effective field theory, lambda squared. And is in the denominator. It has to be in the denominator because in the Feynman rules, it always appears in the denominator, lambda. Okay? So when you compute an amplitude in an effective field theory, typically you need another scale here to compensate for lambda squared. So imagine that you are in effective field theory, you compute an amplitude, you will have something divided by lambda squared, and then to have an amplitude which is adimensional, you need something in the numerator. So this something can be a mass, like the Higgs mass, or it can be something related to the energy. Okay? Now I'm going to the high energy limit, which means that S is equal minus, so S is same order of minus T over 2, which is the same order of minus U over 2. So all invariants are large. Remember, when you do unitarity limit, all invariants have to be large, not only one. Otherwise, it's not the same limit. All invariants large. And then you see that all the same. And now you look at here. Indeed, there is one term which is not problematic. But this term is S to the 4th, energy to the 8th. This one is energy to the 6th. So at the end, this amplitude and I energy is going like S over V squared. S over V squared is not a good behavior, right? Because it has this tendency to grow quadratically with energy, and at some point it will certainly violate unitarity. Okay? So when I ask you which curve is the problematic one, obviously is the one which doesn't have, which grows worse, more intense with energy, is the upper one, right? Because it has this behavior that we don't hit it because the gluon PDF kills it anyway, because you need a lot of energy. So the gluon PDF will kill it. So this is not violating unitarity yet, but is what we call unitarity violating behavior, right? Because it goes up. It goes like it should not go in a renormalizable theory. Okay, is that clear? Yes. Yes. Yeah, no, okay. So you mean that locally it could also be lower? Okay. Yes, yes, it could also be lower because the contribution from lambda is an interference. From the EFT, the contribution from lambda are interferences, and interference can have any sign. But here, this is the squared amplitude, okay? It's not the amplitude, because the operator was dimension 5. So the amplitude technically is actually growing like E over V. Then I square it, and I get E squared over V squared. But then the square is positive, right? So this is not technically a really a consistent. So this is the square of the EFT. If I hope okay. So let me explain it. So when so we have L4, and then we have L6 here. So if I had to compute an amplitude in the effective SMACT, the way to do the SMACT would be that the leading term is 1 over lambda squared, and this is due to the interference of a standard model amplitude with an EFT amplitude. Okay? The leading term. Here looks the same and it's not the same because the operator that we used was dimension 5. So the leading term will be 1 over V, but that will be the interference of the loop with the 3-level EFT, which we are not doing because we are approximating the theory with just the 3-level. Okay, so we are squaring. In this case, it's like we are taking the square of the EFT. Okay, so in our case, we are doing EFT squared, which is lambda squared now, because it's dimension 5 squared. Okay, so so at the amplitude level, this is like this. Okay, so it grows with energy linearly, which is the dimension 5 behavior. So the worst behavior you can have of an amplitude 2 to 2, which has a dimension 5 operator, is grow with energy, because you only want power of V. Now I was talking about the square of it, so that's the reason why I was squaring it. But thank you for your question. This is a very much new point. Did you get it? Do you have any question? Okay. So since this is a square, it's positive, and then it grows. Right? In general, there is a sign here, so locally it can also go down. But then if you sum the amplitude, you square the full thing, at the end it will grow up. Right? If you take the square into consideration. Yes. Here? Yes. So let me expand in EFT the amplitude in the EFT, okay, in a theory where I have a lambda 4 plus, let me put lambda out, okay, just for, so let me write it this way, CIOI. So this is a dimension 6 theory, okay? So these are all dimension 6 operator. Now I compute, so these give Feynman rules, like here. For example, here, right, we have a Feynman rule, which is like this, a new Feynman rule, which is dimension 5. No, okay. So let me use this now. Let me use the full SMEFT. So let me use SMEFT here. So this interaction is actually V over lambda square. So they come from a V over lambda square term. So when I compute an amplitude, right, I have an expansion in 1 over lambda. So I have A0 plus 1 over lambda A6. I don't know, EFT. Okay, which is one insertion, right? So imagine that I have, again, like top, and this is a standard model, and then I modify the coupling of the gluon to the top, right? So this is a standard model. This is a new amplitude with one insertion only, okay? Because that's my scaling. So if I did 2 insertion, I would be dimension 8. Okay, so only one insertion. Then I square this. And when I square it, what I get is A0 squared plus 2 real A0 AEFT star over lambda squared plus this famous or infamous square, because this has kept people busy and still keeps busy in discussions here. So the expansion is like that. So now, technically, in this effective field theory, we only control the theory up to power of 1 over lambda square. So this is higher order. Because it's dimension 8 term, right? Because if I had an operator of dimension 8 here, imagine, right? Would have CIOI 8, and I would put one insertion of this operator, I would have gotten 1 to lambda 4th here. So now the interference will be of this order. Is that clear? Okay. So this term technically is higher order. So technically, I can throw it away. Okay. But the expansion itself is valid when this thing is small. And this is smaller. Right? Because otherwise I'm not expanding 1 over lambda. I'm doing something which I don't know what it is. So you see now that we adjust that, well, so in this case we only computed this one, right? So it's not a good example. But imagine, now I compute this one, and this grows with energy. Okay? So this term here will grow like S over lambda squared. Now, if this grows like S over lambda squared, this guy goes like S, typically S squared over lambda to the 4th. So this grows even faster than this one. But technically, we are always assuming that this is smaller than 1, because we are in the theory, so lambda is our cutoff. We have to be far from our cutoff to have our expansion in over lambda good. So the whole thing makes sense if this is larger than this. Sometimes it's not the case. Sometimes it's actually clear that this is the leading term even though it's suppressed. So then, in practice, it's a lot of if in practice. Okay, but the rule is this one. Now, since we were making an example, we are really comparing two theory independent. We were not computing this one. We're only computing this one, and therefore is our leading term, and that's it. Okay, because we really were comparing two different theory one with the other. Okay. So now I hope I convinced you that by doing this exercise, right, we can use the effective field theory for the top integrated out, so to speak, when the PT is small and for total cross-section. But as soon as we get more accurate and we go higher energies, we cannot use this approximation anymore. However, as someone of you has said, this theory, this effective field theory, the one where now the operator has nothing to do with the top, but is one of dimension 6 operator, is a very interesting one. Okay? So now let's imagine that we work in the standard model. So we have loops, we are super good in computing them, we are not approximating anything. Full standard model. And then we consider the SMEFT with new operators added to the standard model. Okay, so we write what I wrote before, and dimension 6 with new operator. And of course, there are 59 or 2040, 499, depending on flavor. We're not going to, I'm not going to write all of them. So let me write them 3 of them that matters in this business. Okay. So let me write one operator, the first one. So I'm in the standard model, right? I'm here. So one operator that can modify this diagram or this process is when I change the Yukawa of the X to the top quark. So what operator changes the Yukawa of the X to the top? So you write the operator in the standard model. Okay, so I'm using a shorthand notation. When the letter is capital, it means that this thing is left and is a doublet. Okay, like TB, left, and I don't write left. And when I write T, this is T right. Is that confusing enough for you, or? So it is what people do in papers on FT to save space, right? So this is the doublet is left, and this is the right and the top, which is right. So in this case, this thing really, right, will be Q left, I dagger, T right, right, in a normal notation. Okay, but I'm using a compact one. So this operator E plus is a Hermitian conjugate plus a coupling in front, who is the one responsible for the top mass, right? As we said yesterday, phi dagger is 1 sigma 2 phi star, and is the magic trick by Weinberg to give mass to the upper part of the doublet, quark doublet. So how do I? So remember, right? In the standard model, you have minus here yt, and what happens is that when you have phi equal 0 h plus v over square, I'm using the square root of 2, Then this thing, you put it here, you flip it, so you get the t left up there. So you get y over square root of 2 hv times c left, c right, plus c right, c left, which is psi psi, no? For the top. So this piece is the top mass, which now the top mass will be y over square root of 2 v is the top mass. And then I go back here because it's a linear term, so the v and the h are locked together in the standard model. The linear realization of the gauge symmetry. So once I know the mass on the top, I know it's coupling to the x because I get y top, and then from here, this I measure, and from here I put it here, and then I know the coupling of the x to the top. So I call this locking. And it's only me that's calling this, so you don't need to remember. But for this lecture, let me call it locking. What does it mean? I'm locking the Yukawa to the top mass because the coupling of the Higgs to the quark goes through this term where Higgs and V are together, right? Are coupled, locked together. There is no way of unlocking. Okay? So that which we mentioned before. So this term locks the mass to the coupling. There is only one parameter in the standard model. Once you know the mass, you know the coupling. Okay? Is that clear? So now, if I want to change, I want to change the Yukawa independently of the mass. So what do? I unlock it. How do I unlock it? I insert a dimension 6 operator, which is, for example, this one. So this is automatically gauge invariant because phi dagger phi is just, one our most famous operator in the standard model, right? Because it's the one that gives all this problem with hierarchy problem. Is an object which by itself is a singlet of all the symmetries in the standard model, but is dimension 2. Right? It's a lower dimension than everybody else. Is actually leading to the only scale in the standard model. So it's a super important operator. It's also a portal to new physics, right? Because we can compare with other particles coming from outside the standard model. Super important. But here, you realize that you can build basically a copy of the standard model at dimension 6 by adding in front of each operator of the standard model a phi dagger phi. Right? That's the easiest way to promote any operator in the standard model at dimension 6. You just add it in front, and this will be dimension 6. So what does this operator do, really? So the way of thinking about this, one way of thinking, is that it unlocks yt with respect to the mass of the top. Right? You're adding one more coefficient, which I call C phi t, or T phi. Well, let me call it T phi. There are actually two different operators in SMAFT, but it doesn't matter now. So I add this operator, okay, which is the brother or sister of the Yukawa, which is only this one. And what does it do really at the end? Well, again, what I do, I put in the unitary gauge formulation of the X. I look at it in the unitary gauge, and if you see it, right, this thing will give something like hv squared over 2 times the Yukawa operator of before, which was h plus v square root of 2 phi, the phi, let me write it this way, okay, because at that point I'm okay, right? When the symmetry is broken, I can pair left with right. So how do I think about it? Well, now I have this one, which has a new coefficient in front, and I have the old one, right? This one, the one I wrote before. I have both. This from the standard model and this one from the EFT. I have both of them. So effectively, what do I have to do? Well, you see that here there is a term which is like V cube C bar C, which also contributes to the mass. Because the mass, so now if I match this to my theory, so if I predict the mass of the top in this theory, okay, in this theory, the mass of the top comes, it will be this, right? The mass of the top is this definition. So everything which is in front of that, which is constant, is the mass of the top. So everything in front. So you will have minus yt v over square root of 2, which is the old mass, like, right? And you will have plus ct phi over lambda square. Here you have v cube over 2 square root of 2. This term, every other term has a Higgs in it. But there is one which is a constant, which contributes to the mass. Okay, so this thing will be, so now this is the mass of the top. What does it mean? I measure it, and I say from the measurement that this thing here is the mass of the top. It's not this the mass of the top anymore. Then, right, once I have the mass on the top from here, I can trade yt, like before, as a function of the mass, but this time is also a function of this guy. So I trade these two. So I rewrite y as a function of m and c, and I put it here. Okay, so I will, sorry, not here. Let me let me do the other one. So this is the mass of the top, and then from here I look at the linear coupling of the Higgs. So I look at this term, and I look at this coefficient which is in front, and I collect all the linear terms in front. Okay, so from here the linear term will be minus yt h over square root of 2, and from here you see that there are three linear terms. There is a factor of 3. Okay, and then there is ct phi divided by lambda square. Sorry, too many Higgses here. Yeah. Okay. So there is the So the y. Okay. So this is the standard model plus ct phi v square h. Okay. Now that should be right. So there is a fact. There are 2 square root of 2. But okay, I mean, the calculation is the note. I don't care now about factor of 2. So the point I want to make is that this coefficient is in front now of pt bar. So I take it out the h here. So this is the coupling, the new Yukawa coupling. So what I do, I trade mt here for yt, and I substitute yt with another expression, and then I have a coupling of the x, which depends on mt, which is measured, and a new parameter, which is t phi. Bottom line, right? Bottom line, the Yukawa is now a free number. Is an independent number now. Is that clear? So this is a long story. Actually, there is a very effective shortcut to all this story. Instead of adding phi dagger phi q phi tilde t, you add this operator. So you subtract v squared, and now this one does not change the mass on the top. So it makes your life much easier. Right? It's a small trick you use all the time. So in fact, instead of adding this operator everywhere in the standard model, it's easier to add this one because all the zero terms are not changed. So all the standard model interaction and masses and so on are not influenced. Otherwise, you have to do this trick, which I wanted to show you because that's always what we do in this method. We redefine the coupling. But at the end of the day, it means that the coupling here is unrelated to the coupling in front of the interaction. So I have unlocked y and t. So y and mt are now two independent parameters. So a long story, a lot of algebra for just saying at the end, well, just put a different coupling for the y, and that's within the realm of this math. However, and this is very important, okay? However, there is something which you might have noticed now, which is absolutely non-trivial, that we have to keep into account, and is really now a prediction of this math. So far, right, what I could have taken my standard model Lagrangian and say, look, take yt arbitrary, and that's it. Okay? I made all this complication for what? I mean, at the end, I write it in the broken phase, and then I take yt different from mt. That's it. There's no, look, on this respect, there is nothing else happening. But it's not true. There is much more happening, right? Why? Because here, now, this is the linear term. But from here, right, when only one of these is a vacuum expansion value and the others are x's, you have terms like x squared phi dagger phi, phi bar phi, and you also have x cube phi phi. No? By developing this polynomial, h, so by developing h plus v to the cube, you get all these interaction, right, with different powers of v, okay? So here you have no power, so this is dimension 6. So here, this is dimension 6, right? So there is nothing in front. This is dimension 5, so you have 1 power of v in front, and so on, right? So you have two other terms, and when these terms, these interaction, are not there in the standard model, are new interaction, because you see, this dimension 5 doesn't exist in the standard model, but you also have this one. So it's also this is new. Okay, so the result of introducing the full operator, this one at dimension 6, is that I also generated new Feynman rules, which were not there, which go beyond separating these two, and are mandatory because the coefficient of these two are both depend on Ct phi. So they are locked to this You see? So I unlocked MT from YT. Is separated now, but I introduce other two Feynman rule which are locked to YT. Okay? So I only, with dimension 6, I was able to unlock these two, but not to unlock the other one. Everything is now locked to YT. So if I change the Yukawa of the top, and for example, I produce two Higgses, I cannot forget this diagram. I have to put that diagram, to put this rule. Right? For single Higgs, doesn't matter. But if I produce two Higgses, which will be the next thing that we'll talk tomorrow at this point, I need this one at dimension 6. If I want to unlock the change in YT from this one, I need a dimension 8 operator. If then I want to unlock this one from this one, I need a dimension 10 operator. You see? So the EFT is predictive still, right? The fact that you are adding this operator and you're not changing these two by hand, it will not make any difference in single Higgs cross sections. But if you have your full theory where all your data with double Higgs, for example, then it's different. Having just done this or done the full gauge invariant thing. Okay? So, remember, so what I want to say, and then I'll stop, is that this feature is actually a property of the standard model and of adding a dimension 6. So in the standard model, right, for example, mass of the Higgs is 2 lambda v squared, right? So when you do the potential, remember, right, the mass of the Higgs is related to lambda. So lambda regulates the 3 and the 4 point interaction of the Higgs. Okay, so it means that once you know the propagator of the top of the Higgs, which means once you know the 2-point function of the Higgs, which means the mass of the Higgs, you know all the coupling, self-coupling of the Higgs. So I call this locking again. When I know the mass of the Higgs, I know the interaction. And for the W, right, and the Z, right, is the same. Right? Once, so this is a W, let's say, okay? So once I know the mass of the W, so I know the 2-point function for the W, I also know the coupling of the W to the Higgs. This is fixed because this one is mass of the W squared divided by V, and this one is mass of the W squared divided by V squared. So once I know the mass, I know the coupling. The physics in the standard model is locked. And that's why, and this is equivalent to say, right, that masses interact, the strength is proportional to the mass. That's the usual way we phrase it in courses. And for the fermion, it's the same. The mass of the fermion is equal to 1 square root of 2 y v. But then the fermion interaction with the Higgs is locked because it's m over v. Knowing the masses, you know all the interaction in the standard model, like in the electroweak sector of the standard model. So what happens if you add a dimension 6 operators in general, like this one? What you do, you break it. You break it here. So now you separate the masses from the interaction, like what we did now, I call this unlocking, right? In this scheme, right? I open my lock here. So with dimension 6, I'm opening it here, but I'm not opening it here. That's the big prediction of SMAT and dimension 6. These things are still connected in a unique way, right? So in the standard model, there is no double Higgs interaction, right? But in the EFT, there is, right? And what we said is that this interaction is related to this. And dimension 6 is also true that this one is related to this, and this one is related to this. Because you add one parameter more, not two, just one. And that means that these two are still locked. So here, they're still locked. Okay? Here. So if you want to unlock this, you have to add dimension 8 operators. So this is a graphical way of thinking about what a dimension 6 operator do in the standard model. Of course, there are many, so they also introduce new interaction that were not there, so it's much more complex than that. But on the standard model coupling, this is what it is, really. Okay? This is what happens at dimension 6. Okay, so then let me stop here, which is a good moment where to stop. Thank you.